All right, let's get started with chapter 12, 12.1, Introduction to Limits. So, a limit is kind of a basic building block for calculus, so we're going to get started with some calculus topics, the final chapter we're going to deal with this year. So, let's start with an example first, and then we'll dive into the concepts. So, you're given 24 inches of wire and are asked to form a rectangle whose area is as large as possible. Determine the dimensions of the rectangle that will produce a maximum area. All right, so we're talking about area, and we know that area is length times width, and the area here has to be 24. We know that, we're maximizing the area. We know that the perimeter has to be 24, so we know that 2 length plus width has to add up to 24 here, so we know that the length plus the width has to equal 12. All right, so the one thing we could do here is using substitution say that the length is going to be 12 minus W, and now we can rewrite our area formula as a formula with only one variable, just W in it. So 12 minus W times W, and if we expanded that, we could have 12W minus W squared. All right, so how do we maximize that? A couple ways to think about this, and let's grab our calculators. Oops, where's our calculator? There we go. All right, so I'm going to go into the y equals and plug this in. 12w, we can use 12x minus x squared. All right, and let's change our window, make sure it's good. That looks pretty good. Let's graph it. Goes up and coming back down further on, so I'm going to need to zoom out here. And let's go with negative 10, how about to 25, see what happens there. All right, it's coming down now, and then I'll do a zoom fit. There it is. To change my y values so we can see the top here. There we go. All right, so I just want this area here. The top there is 35. So let's change this back up again and say, how about negative 5 to 40? And now we'll have a nice graph here. All right, so clearly the area is maximized right here. So we could go ahead and find that maximum. And if we go ahead and use our trace feature, we can move over here. And it looks like, just by moving back and forth, it looks like about 6. An area of about 6 is going to maximize this. So let's go ahead and use a table here and see if we can confirm that. So I'm going to type in 5.5 and count by 0.1. So put it back into auto mode. And let's go to the table and see what happens. At 5.5 we get 35, 0.75, we count up, count up. At 6 we get 36, and on either side it is going down. So clearly here from the table, and we're going to use tables a lot in this chapter, we can see on the table that it's increasing as we approach 6 from below 6, and it's increasing, the y values are increasing as we approach 6 from x values bigger than 6. So here we are going to say that the answer is 6. So the maximum would be the width is 6. All right? And the other thing we can say here is that the limit as w approaches 6 for our area is going to be 36. The area is 36 as w gets closer and closer to 6. All right, go ahead and try problem 5. Okay, so estimating a limit numerically. So we're going to go back to our graphing calculator again on this. We're going to use a table to estimate the limit of 3x minus 2 as x is getting closer and closer to 2. So that's how we read this. This is the limit of f of x as x approaches c. And we'll get some answer. All right, so calculator, y equals, we're going to type in the function, 3x minus 2. And we want to know what happens as x is approaching 2. So we're going to go to our table, and we're going to change our table start to a little bit below 2, like 1.7. And we're going to check the table. And here, it looks like, as we're getting closer and closer to 2, the y values, that's what we care about, are approaching 4. So our answer here would be the limit as x approaches 2 of 3x minus 2 equals 4. All right, so using that information, try exercise 7. Okay, so now let's talk about where limits really become useful here. When we have a problem, so what's the limit of this function as x approaches 0? So you'll notice, look at the denominator here. If we plugged in 0 to the denominator, oops, minus, the square root of 0 plus 1 is the square root of 1, which is 1. Minus 1 is 0. Normally we would not be able to do this problem because you can't divide by 0. So what we're asking ourselves, though, is not what happens at 0. We want to know what happens as we get close to 0, not at 0. All right? So that's the distinction with the limit. So let's go ahead and do exactly what we just did. Plug it into the calculator. Y equals x divided by, make sure we're putting this in parentheses, square root of x plus 1. And we'll close our parentheses there, and minus 1, and close our parentheses again. Let's go to our table set and make this a little bit less than 0, negative 0.3, and the table. And you can clearly see we've got an error here, right? But what does it look like our numbers, if we blank this out and just forgot about the error for a second, what does it look like our numbers are getting closer and closer to, coming from both directions? And the answer is 2, 1.8, 1.89, 1.9, 2.1, 2.09, 2.04. Looks like we're getting closer and closer to 2. And so that's going to be our answer here. The limit here is 2. Go ahead and try problem 9. All right, so estimating a limit here. So in example 3, note that f of x has a limit even though when we go to x equals 0, we're undefined. All right, so this happens a lot, and it's important to realize that the existence or non-existence at x doesn't matter at all. All right, so let's go ahead and try one more. This is another case on this one. X minus 1. 1 minus 1 gives us 0. We can't be at 1, but what happens as we get close? Y equals x cubed minus x squared plus x minus 1 all over x minus 1. And we'll go ahead and use our table, starting a little bit below 1. And it looks like 2 is our answer. Now, on example 4, I'm going to do a graph here for the first time. Let's go ahead and change our windows back to something reasonable. Actually, we can go -1 to just 1 here. And our y values, let's go -5 to 5. Because we know our answer here from our table is going to be somewhere around 2. So those seem like decent numbers. So as we graph here, as we zoom into 1, as we use our trace, as x becomes 1, left, oops, I need my window a little bit bigger. Let's go to 3 here. Notice that right there, if you zoom in at 1 when x is 1, there's a little hole there, right? We can't be at x equals 1. So when you graph these, sometimes you're going to have holes, which we'll denote with a little circle when we graph them, all right? But that doesn't matter because we can still get very close to that point even if we can't actually be there. So go ahead and see if you can use a graphing utility to figure this one out graphically. So see if you can graph it and figure out what the limit's going to be by looking at the graph. Okay, so you can see the graph here, and your answer is going to be 1/4. All right, now what happens if we have a piecewise function here? Let's go ahead and find the limit of this. So we're going to do this without using the graphing calculator. We're just going to put it up here. So when x doesn't equal 3, so everywhere except for at this point right here, y is going to be 2. So we have a horizontal graph, except for we'll have a hole right there. And when x is 3, instead, the y value is going to be 0. All right? So what's the limit as x approaches 3 of that function? Just write f of x instead of rewriting it. The answer here is 2. Even though when x equals 3, y equals 0, as we get close, the limit means as we get close, the y value is 2. So the limit value is going to be 2. See if you can use the same thinking for 27. All right, so we're going to have 3 examples here. Examples 6, 7, and 8 all don't work. All right, so let's show that the limit does not exist. All right, so back to the graphing calculator. Y equals, clear this out, the absolute value, which is in math, I believe. Where are you? There it is. Absolute value of x divided by x. And let's see what happens as we approach 0. So we'll change our table set to a little bit less than 0. And notice here, so to the left of 0, when the x values are negative, the y value is -1. And then, as soon as the x values become positive, the y values are +1. If we graph this, look what happens. We've got from the left, as we're approaching from the left, the y values are -1. As we approach from the right, the values are +1. So, rule number 1, if the approach from the left does not equal the approach from the right, no limit. All right? So graphically we can say that we can show that this limit does not exist. All right? So, use the graph to explain why this limit doesn't exist. All right. Second bad situation where the limit's not going to exist. Let's graph this. 1 over x squared. I'm going to expand our window range a little here. All right. As x is approaching 0 from the left, it takes off and goes to infinity. As we approach 0 from the right, the y values take off and go to infinity. All right? We will never, ever, ever get to a value if x is 0. This is what's called unbounded behavior. All right? So if we have an unbounded behavior at the x value, the limit does not exist. All right? So same thing with 33. Tell me why it doesn't exist. And last situation where the limit will not exist, sine. I'm going to make sure we're in radians here. Our good friend sine, haven't seen him in a while. Sine of 1 over x. And go ahead and graph that. And I'm going to zoom in with a zoom box around 0. And it looks like some action's happening starting about there. It's starting to curve. So I think that's a pretty good starting point. Let me scroll over to where it starts to flatten out again. Right there. All right, so as we're approaching 0 here, notice that our value is going up and down. It's what's called oscillating. And if we're oscillating, okay, going up and down, then we're not going to have a limit either. All right, so last thing here, we can see right away on 35, this limit does not exist at 0 because we have oscillating behavior. All right, so those written down are the 3 reasons we're not going to have a limit. You can pause this and get those down. Examples 6, 7, and 8 described all 3 of those. Get those, and we're going to move on to properties of limits. Last 2 examples. All right, so direct substitution means that If we are approaching some number, we can plug that number straight in, and that will be our answer as long as we can evaluate it at that point. All right, so a couple rules here to write down. Get those in there. And then a couple more properties, and these are very effective if we're going to do, say, the product of the limit of two things multiplying. What this means is we can do the limit of the first function times the limit of the second function. And that works all the way through. All right, so let's take a look at a couple examples here. Find each limit. All right, so we're going to use direct substitution for all of these. So this is A is going to be 4 squared is 16. B is going to be 5 times 4, which is 20. C is going to be tangent of pi divided by pi, which is 0 over pi, which is 0. The D, the limit as x approaches 9 of the square root of x is just equal to the square root of 9, which is going to be 3. As long as we're doing a function, we're not going to worry about plus or minus there. E, what is pi times the cosine of pi? That's going to be pi times -1, which is negative pi. And last one here, 3 plus 4 squared is 7 squared, which is 49. All right, so if you can plug in the x value, plug it in. Those are the easy problems. We like it when that happens. So go ahead and knock out A, B, C, and D for 47. Give that a shot. And last example here. All right, so for limits here, if p is a polynomial, we can still do direct substitution. If it's a rational function, something divided by something else, we can still do direct substitution as long as there's no 0 in the denominator. All right, so find each limit. We're going straight to direct substitution. -1 squared plus -1 minus 6 is 1 minus 1 minus 6, which is -6. And we can still do this because -1 minus 3 in the denominator is allowed. As long as x doesn't equal -3, we can do this via direct substitution. Over -1 plus 3, we already know that we've got -6 on top, and we've got 2 on the bottom, which is -3. All right, one last problem to try for you here. 51, knock that out, and you are done with 12-1.